Hey, today we're going to talk about a summary of curve sketching. This is going to pull together all the information that we have from the original function, first derivatives, and second derivatives to allow us to see what a graph looks like without using a graphing calculator. That's cheating, people. From the original function, we can determine the domain and range. The domain of the function is all x values that you can use, and the range is all y values that are output by the domain values. We can determine all intercepts. Recall that the x-intercepts are when the y value is 0, and the y-intercepts are when the x value is 0. We can determine all asymptotes if a function has them, vertical asymptotes and horizontal asymptotes. We can determine any symmetry of the graph if this will help us graph it. This is very useful when we're graphing trigonometric functions. The most important thing you can remember about the original function is that you always use the original function to find any y value for a point. The first and second derivatives will give us some important x values to look at, but we always go back to the original to find the y value when we're entering a point. Speaking of the first derivative, from the first derivative we can find critical numbers. Critical numbers occur where the derivative is equal to 0 or where the derivative is undefined. However, this still has to be in the domain of the original function. If the derivative is undefined and that value is not in the domain, we do not call it a critical number. Frequently, that is an asymptote, as we'll see in this example. We're going to use these critical numbers to break up the real number line into intervals. Once we have those intervals, we'll take test points to check each of those intervals for increasing or decreasing of the function. We'll use a theorem that states that a function is increasing where the first derivative is positive, which makes sense. The slopes of the tangent lines are positive, they're going up. And a function is decreasing where the first derivative is negative, so the slopes of the tangent lines are decreasing. With these intervals, we can also determine any maximums or minimums, any relative maximums or minimums, if a function has them. From the second derivative, we find possible points of inflection that occur where the second derivative is equal to 0 or the second derivative is undefined. Once again, these points still have to be in the domain of the original function, even if they're undefined in the second derivative. Possible points of inflection, very similar in the second derivative way of critical numbers as associated with the first derivative. The possible points of inflection allow us to divide up the real number line into intervals. Once we have these intervals divided up, we use test values to determine which of these intervals are concave up, so the second derivative is positive when the graph is concave up, and which make the graph concave down, indicating the second derivative is negative. We could also use the second derivative test in order to determine relative maximums and minimums if for some reason you didn't use the first derivative test. Let's take a look at an example. In order to graph these, we're going to sketch in all asymptotes and intercepts to provide a framework. We're going to use the critical numbers and find critical points by evaluating the original function. We'll do a rough sketch indicating increasing or decreasing just to give us an idea of what's going on. I like to use simple arrows, increasing or decreasing, to give me an idea. We'll then use the x values of the possible points of inflection to find actual points of inflection by evaluating the original function, always going back to the original to find y values. We could do a little sketch of concave down, a little sketch of concave up in the region to let us know where things are. And from there, possibly with a few extra points just for specifics, we should be able to render an accurate sketch of our graph. Let's look at this rational function. We're going to sketch the graph of f of x equals 3 minus x divided by 2x plus 1. First, we start with the domain. In the domain of a rational function, we're going to look at the denominator. We know the denominator cannot equal 0. So I take 2x plus 1 and I set it not equal to 0. I'm going to subtract 1, divide by 2, and I get my domain of x cannot equal a negative 1/2. Because negative 1/2 is not a factor of this numerator, we know that this domain value that must be excluded is also a vertical asymptote. Notice that my vertical asymptote is written as the equation of a line. all asymptotes are lines. All lines must be equations. They must have something on the left, an equal sign, and a value on the right. To say -1/2 is the vertical asymptote is incorrect. You must have x equals -1/2. To find the x-intercept, we set the entire function equal to 0. But when we set a rational function equal to 0, our first step is to multiply both sides by that denominator. So finding x-intercepts of rational functions turns into finding where the numerator is 0, but the denominator is not. Since this one does not have any common factors, we just worry about where 3 minus x is equal to 0. We can add x to both sides. X equals 3 is our x-intercept, but I prefer to put it in point form. 3, 0, the x value of 3 gives us a y value of 0. To find the y-intercepts are easiest. We make our x values equal to 0. And when our x values are 0, we're left with our constant terms, 3 over 1. So we have our y-intercept is also 0, 3. So our intercepts are both at positive 3. To find the horizontal asymptote, we can look at the limit as x approaches infinity. If you would like to do it the long way, you could divide everything by x. Let x approach infinity, let x approach negative infinity, and you will find your answer. Or, from pre-calculus, we learned that when the powers of the numerator and denominator are equal, in this case they're both linear, we can look at the leading coefficients, -1 divided by 2, to give us the horizontal asymptote. Once again, the horizontal asymptote is an equation of a line, so I must have y equals, because it's horizontal, the -1/2. Let's move on to the derivative. In order to find the derivative of this function, we have to use the quotient rule. The quotient rule states, in a very sing-songy method, low derivative of high minus high derivative of low all over low squared. The low in this case being our denominator, 2x plus 1. Derivative of high is a -1, minus, always a minus. High, 3 minus x, times the derivative of low, derivative of the denominator is 2, all over the denominator squared. Multiplying -1 by my 2x plus 1, I get -2x minus 1. I'm multiplying 2 and a negative times my 3 minus x, so I get a -6 and a positive 2x. My 2x's cancel, and I'm left with -7 divided by 2x plus 1 squared. When I see this, I notice two things. First, I notice the numerator will always be negative. -7, always negative. And I notice that my denominator is squared. And for real numbers that are squared, this will always result in a positive value. Positive or 0, so let's call it non-negative. So I kind of know that for any x value that I can actually plug in, my first derivative is going to be negative. If you don't notice that, that's all right. We'll get to it down below. The first thing I notice, the f prime of x is never 0. If we set this equal to 0, we're going to multiply both sides by a denominator. -7 is never 0. The numerator is never 0. So the derivative is never 0. The first derivative is undefined. At the same value, we had to exclude from the domain. Now, the first derivative undefined, we're thinking critical number. However, because it is the same value we had to exclude from the domain, this is not a critical number because this is not a part of the domain of the original function. I can still use it, however, to break up my number line into two intervals, things to the left of -1/2, smaller, and things to the right of -1/2, which are larger. I'm going to pick any number that's to the left of -1/2. -1 seems like the easiest value. When I evaluate f prime at -1, I'll end up with a -7 divided by -1 all squared. -7 divided by 1 gives me a negative result. The fact that it's a -7 doesn't matter to me at all. The fact that it's negative is our key. Picking a test point to the right of -1/2, I'm going to use the easiest test point ever. I'm going to use 0. F prime evaluated at 0 will give us -7 over 1 all squared. That's a -7 over 1, which is also a negative result. This tells me the graph always decreases. But we can't say it decreases negative infinity to positive infinity because there is this break at the asymptote x equals negative 1/2. We must break our interval as we have it on our test points from negative infinity to negative 1/2, unioned with negative 1/2 to infinity. Because this only potential critical number is not in the domain of the function, there is no relative maximum or minimum for this particular function. Moving on to the second derivative. Rather than using the quotient rule, I've chosen to rewrite my first derivative so that I can use the chain rule. The chain rule tells me I leave my coefficient of negative 7 alone, I bring down my negative 2 and multiply, giving me a positive 14. Leave the inside alone, subtract 1 from my exponent, and then don't forget to multiply by the derivative of the inside, the derivative of 2x plus 1 being 2. Simplifying, 2 times 14 will give me 28 in the numerator, and 2x plus 1 to the third power in the denominator. Once again, my second derivative can never equal 0 because 28 is my numerator, 28 can never be 0. The second derivative is also undefined, x equals negative 1/2. The original function, first derivative, second derivative, all undefined at this value of negative 1/2. Even though it cannot be an inflection point, since it's not in the domain, we do use it to break apart our our number line into intervals. Checking values to the left of negative 1/2, I once again use an easy value of negative 1. Substituting into my second derivative, I find that I have 28 over a negative 1 to the third power, which will be negative, so I'm concave down on the left. I use my easy test value of 0. F prime of 0 equals 28 over 1 cubed. Both numerator and denominator are positive, so the quotient is also positive, and we're concave up. Reporting this, the graph is concave down to the left, negative infinity to negative 1/2, and concave up on the interval from negative 1/2 to infinity. Just as a reminder, there are no inflection points. Even though the graph changes inflection, negative 1/2 is not a point on the actual graph. Let's see what happens when we put this all together. I start with my intercepts. My intercepts are at 0, 3, and 3, 0. I move on to my asymptotes. Asymptotes is dotted lines, x equals a negative 1/2, and my horizontal asymptote, y equals a negative 1/2. I indicate that it's decreasing in these two areas, both to the left and to the right of my negative 1/2. And I do a quick sketch of concavity to show it's concave down over here, concave up on the right hand side. This reminds me of what I should be drawing as I draw my graph. Now on the right, I can kind of see, because it's a rational function, I have an idea what they look like. I know it approaches my asymptote on the left side of the graph, the right side of negative 1/2, the left end of this piece of the graph. It looks somewhat like this. May or may not have hit the actual intent here. Let's take a look. If I put in 1, 3 minus 1 is 2. If I put in 1, 2 plus 1 is 3. So I should be at 2/3. Looks like this is a bad graph, people. It should come more like this. I'm a big fan of close enough is good enough. You get the right idea of what's going on. To get any values on the left, we have absolutely no points whatsoever. We know it's concave down, we know it's decreasing, but where and how? I use test points, actual points, excuse me, not test points. Evaluate the original function at negative 1. I'll have 3 plus 1, which is 4. Negative 2 plus 1, which is a negative 1. 4 over negative 1 will give us a negative 4. I also used a value of negative 3 to give me a negative 6 over 5. I'm starting to think that maybe, since this graph was so far off, I should use a negative 2 as well. 3 minus a negative 2 is 5. 2 times negative 2 is negative 4. Negative 4 plus 1 is 3. So I have a negative 5/3. Yep, this graph is a little off as well. I missed my point there, but I got pretty close. Approaching my asymptotes on both ends of this piece. Here we have the graph of f of x equals 3 minus x divided by 2x plus 1 using the original function, the first derivative, and the second derivative to find relevant features of our graph. Thank you for listening.